So, good morning. Today we will discuss and introduce MOS transistors, the devices which can be fabricated thanks to semiconductor technology and which are the essential elements of any integrated circuits, in particular in any digital integrated circuit. And we will discuss how these devices, which in digital electronics are used as voltage controlled switches, can be used in digital gates which implement fundamental Boolean functions. So today we will start discussing the semiconductor technology, which is based on the properties of semiconducting materials, in particular silicon. We will see how, starting from this technology, we can implement MOS transistors. Then we will discuss the electrical properties of MOS transistors, and we will outline their possible operation as a non-ideal voltage controlled switch. That is what we need in digital electronics. And based on that, we will discuss how digital circuits which implement basic Boolean functions like the NAND or the NOR function can be developed starting with MOS transistors. Then we will introduce also different types of digital gates in the same semiconductor technology, which make it possible to basically overcome the limitations of standard CMOS gates when connected to distributed interconnects, that is, bus structures. Okay. Now let's start from integrated circuit technology. Actually, integrated circuits are fabricated starting from a wafer of silicon that has basically this aspect is a single crystal of silicon semiconductor material, on which, thanks to photolithographic techniques, is possible to define the geometries both of the active devices, the transistors that we will discuss today, and of the interconnects that are needed to implement the circuits that we will discuss today. Actually, thanks to this technique, it is possible to design single devices which have a size in the nanometer range, so they can be extremely small, and as a consequence, it's possible to integrate a billion of devices on the same wafer. The integrated circuits that are fabricated in these techniques are then can be cut individually, can be sliced individually. Then they are put in a package with electrical contacts that make it possible to get access to specific terminals inside, input and output terminals inside the circuit. And these packages in the end can be soldered and interconnected to other integrated circuits and other passive devices on a printed circuit board. This is how basically electronic systems, present-day electronic systems looks like. By the way, the heart of these systems are the transistors which are integrated on the chips obtained on the silicon wafer. Now let's discuss more on the property of about the properties of silicon and how it's possible to obtain transistors in this technology. Actually, silicon is an element that belongs to the fourth group in the periodic table. It means that it has 4 free electrons in the outer shell, which can be which are suitable to create bonds with other atoms. In a crystal, in a silicon crystal, in a single silicon crystal, as the ones which are used for the fabrication of integrated circuits, we have that each silicon atom is bonded with 4 silicon atoms nearby, and in each bond, one of the 4 electrons of the outer shell are shared with a neighbor atom. Okay. This structure, from an electrical point of view, can be regarded as a semiconductor. It means that it's neither a good conductor like a metal, but it's not also an insulating material like glass or ceramic materials. And what's particularly relevant for electronic applications is that by replacing in the crystal structure of silicon one atom of silicon when another atom of a different element, which belongs either to the 5th or to the 3rd group, means with 5 external electrons or 3 external electrons, it's possible to vary the conductivity and the electrical characteristics of the material. In particular, when we replace a silicon atom with an atom of an element of the 5th group, for instance, arsenic, the arsenic atom replaces the silicon atom, but since it has 1 more electron in the outer shell compared to silicon, it happens that the arsenic atom in the crystal becomes a positive ion, and the extra electron in the outer shell becomes a free charge that is free to move in the crystal, and can give rise to current flow when an external electric field is applied. Okay. So these free electrons, by replacing some silicon atoms with an arsenic atom, we increase the density of these free electrons, and in the end we can increase the conductivity of the material. This, by so doing, we replacing using an atom of the 5th group, we generate negative free charges, electrons, and we say that the material, the silicon, is doped with n-type doping. On the other hand, it's also possible to replace one silicon atom with an atom of an element of the 3rd group, like boron, for instance. Boron is characterized by 3 electrons in the outer shell, which means that when replacing the silicon atom, the boron atom has to get an extra electron to act as a silicon atom in the bonding, and so in the end, this replacement gives rise to a missing electron in the crystal structure. So the boron itself becomes negatively charged, becomes a negative ion, and the free missing electron in itself is called a free hole, and like electrons, it behaves as a free charge, a moving charge, a charge that in the presence of an external electric field can be displaced and gives rise to current. When we add dopant of this kind, the third group, we say that the silicon is doped with a p-type material. Both free electrons and free holes contribute to the conduction current, but it's worth being stressed that these two contributions are inherently different, since they are two different currents with two different natures, electron current and hole current. This unique feature of semiconductor materials with p-type or n-type doping gives rise to specific and unique behaviors when we have a p-type and an n-type region that are basically adjacent, that are that are basically obtained on the same crystal and in adjacent to the one to another. When we have this structure, we say that we have a p-n junction. This is a p-n junction, and from an electrical point of view, it behaves as a diode. It has also its electrical symbol, that is the one reported here in the slide. It resembles an arrow. Basically, the p-type area corresponds to what is called anode of the diode. The n-type, the n-doped area corresponds to the cathode, and the special feature of this structure, actually from the electrical point of view, it can be regarded as a two-terminal element to which, for instance, an external voltage VD can be applied. What can be observed that due to the different nature of the electron and hole current, when we apply to this junction, to this structure, a voltage that is positive on the P side of the junction and negative on the N side, if it exceeds a voltage of about 0.6, 0.7 volt, we have conduction, we have a strong current flowing through the junction that increases exponentially with the voltage VD that is applied. On the other hand, if we apply a voltage VD with an opposite polarity, that means a negative voltage with this convention, a voltage that is positive on the N side of the junction, positive on the cathode, and negative on the anode, we have that no current flows through the junction. Actually, the full relation between the applied voltage and the current flowing through this structure, to this p-n junction that is called p-n diode, is given by this expression. So actually we have that the current is proportional to a constant that is related to the dimension of the junction and to the technology, that is IS, times a factor that is an exponential factor of the applied voltage VD, divided by Vt, which is a physical constant. Vt actually is kT over Q, where K is the Boltzmann constant, T is the absolute temperature, and Q is the electron charge. You can note this -1, thanks to this -1, when for Vd equal to 0, we have that Id is equal to 0 as expected in a stable system. Okay, So basically, when we apply a reverse bias, that is, we apply a voltage which is positive on the cathode and negative on the anode, we have approximately no current, and we say that the junction is reverse biased. On the other hand, when we have current flowing through the device, due to this exponential relation between voltage and current, the current can flow just from the anode to the cathode, that is from the P side to the N side, and the voltage across the diode remains almost constant. The voltage VD remains positive and almost constant even when the current ID increases very much. Okay. Actually, these junctions are the key elements which are exploited in more complex devices that are MOS N-type and P-type transistors, which are actually the key components which are needed and used as voltage controlled switches in digital integrated circuits. Let's discuss in detail what is the structure of an N-type MOS transistor. Actually, we start from a silicon wafer. Actually, I am showing the cross section here, so you suppose that this is the thickness of the silicon wafer, which is made by P-type doped silicon, P-type doped silicon. This bulk silicon is called the substrate. On this structure, we have two regions which are doped with N-type dopants, and they are strongly doped. This N plus means that they are strongly doped with a high concentration of dopants, so that to become highly conductive like contacts. These two regions are called the source and the drain region of the transistor, source and drain region. Actually, the substrate itself is also can be also contacted by contact with a P-type doping, that is typically also surface contact like this, and is called the bulk or body contact. Okay. In an NMOS transistor, the voltage of the substrate that can be biased through the bulk or body contact is chosen so that to be higher than, to be the lowest available voltage. So in particular, the voltage of the source and the voltage of the drain terminal are both larger than the voltage of the bulk. So this is VSB, and it is positive, and VDB is also positive. It means that these junctions between the source and the body and the drain and the body are supposed to be reversely biased, and so no current, the current flowing from the source to the bulk or from the drain to the bulk is almost negligible. Okay? On the top of this structure, so these two terminals, which are actually represented also in the symbol of this device. This device is also characterized, this structure is also characterized by its own electrical symbol, which is like this. Source, this is the this is the source, this is the drain, and this is the body contact. Well, this over this structure, in which, without adding anything else, we have said that the source and the junction between the source and the body and the junction between the drain and the body are reverse biased, so no current flows from the drain to the body or from the source to the body, and no current flows from the drain to the source or vice versa. On the top of this structure, what is done is to add basically a structure which resembles a capacitor. So here there is a thin layer of silicon dioxide, which is an insulating material, and on the top of this insulating material we have a metal plate, a plate that can be made of true metal or highly doped silicon, which actually behaves as a conductor, so as a metal. This top terminal is called, this top plate is called the gate of the transistor, and actually it corresponds to the gate terminal in the symbol. Well, the idea is that this structure, which resembles parallel plate capacitor, in which we have the gate that corresponds to the top metal plate, we have the silicon dioxide, which is the dielectric, which is the insulator, and the bottom plate is actually made, is the bulk, is the body of the semiconductor material. This structure can be regarded as a parallel plate capacitor. When we apply a voltage between the bulk and the gate, with the positive on the gate, typically to work properly, also the source should be connected to the bulk, or should be at a voltage which is lower than the applied gate voltage. When we apply this voltage, basically we induce a charge on the two plates of this, suppose this is contacting the bulk, we induce a positive charge on the metal plate and a negative charge on the semiconductor plate of this capacitor. This negative charge is actually made of electrons, while the holes that are the carriers which are responsible for the conductivity of the substrate of the p-type doped silicon cannot cross the N junction and give rise to conduction between the source and drain terminals in the original case, when we have this channel of negative charges of electrons on the bottom plate of this structure, these charges basically, thanks to these charges, there could be a current flowing from the drain to the source. So we can have a current. There is a conduction between the drain and the source of this device. Okay? But this happens only if we apply a positive voltage on the gate. In other words, if we apply a positive voltage on the gate, we have conduction between drain and source. If the voltage between the gate and the source is not applied, actually we will see if the gate voltage is less than a certain quantity that is related to the technology, which is called the threshold voltage, what we have is that this conductive channel is no longer there, and there is no conduction between the drain and the source. This is the, in short, the physical principle which is exploited in an MOS transistor. When this conductive channel is created, basically the transistor is with for voltage, gate voltage larger than the threshold voltage, the transistor behaves as either as a resistance or better as a non-linear resistance between the drain and the source, and in any case it's possible to have current flowing through the drain. Okay? Actually, this is the full symbol of the NMOS transistor. In digital electronics, the body terminal of an NMOS transistor is always connected to the lowest potential of the circuit, and for the sake of simplicity, it is not indicated in the symbol. In the symbol, we have just the gate, the source, and the drain. And the quantity that basically controls the conduction state of the device is the voltage between the gate and the source. Okay? This is the symbol used in digital electronics. Okay? In this symbol, it is assumed that the bulk is connected at 0 volt. That is the lowest potential in the circuit. In this symbol, you may observe that the MOS transistor in itself is symmetric. By the way, we can differentiate between the source and the drain, since the source is the terminal between the source and the drain at the lowest potential. So the source is at lower potential by definition. So we have that Vs is less than Vd in an NMOS transistor. Actually, this is just one of the possible type of transistors which are available in present day MOS technology. We also have a complementary device that is obtained starting from no longer from p-type doped material, but from an n-type substrate, in which we have complementary dopings. So we have p plus source and drain regions, and we have an N plus bulk or body contact. In this case, we have that the body is at the highest available voltage, typically at the supply voltage, and so the PN junctions that we have between the drain and the body, between the source and the body, are also in this case reverse biased. So there is no current from the source to the body or from the drain to the body. Also in this case, we have a structure that is made by gate, a conductive material, and which is separated from the surface of the semiconductor by silicon dioxide, which is an insulator. So we have a conductive plate that is the gate, we have the insulating material, and we have the bulk semiconductor. Note that the acronym MOS transistor, MOS, stands, describes actually this structure both for the N-type and P-type device. So it describes the structure made by metal oxide semiconductor. If you take the acronym, you get MOS. Since this structure behaves as a transistor when an electric field is applied between the gate and the bulk, the full name of the device is metal oxide semiconductor field effect transistor. So the full name is MOSFET. In short, MOSFET. In short, MOS transistor, N-type MOS transistor, or what we are discussing now, P-type MOS transistor. The structure in which we have start from the N substrate, we have P plus source and drain contacts, is called P-type MOS transistor, P-channel MOS transistor, or simply PMOS transistor. The symbol in this case is similar to the previous one, but the arrow that represents the bulk is in the opposite direction. Then another difference is that the terminal at the higher potential is now the source. So here we have the source. This is the bulk, and this is the drain at the lower potential, and always the gate in between. Compared to the NMOS device here, in order to establish a conductive channel between the drain and the source, we need to provide 3 positive carriers to establish the conduction between these 2 P-type doped regions. We need holes, we need extra holes in this channel, and for this purpose we need to apply to the gate a voltage which is lower than the source. Typically the source is tied very often to the bulk at the highest possible potential, VDD, and we need to apply a lower voltage to generate to create a conductive channel made of holes on the surface of our semiconductor material. Okay, so if we connect also the gate to a high voltage, this is, we do not have any conductive channel, but if we apply a voltage to to the gate that is negative, so we have source gate voltage positive, that means that the gate is at a lower potential, sufficiently lower potential compared to the source and to the bulk, we induce these positive charges on the surface under the silicon dioxide, on the surface of the silicon, and thanks to this channel, the drain and the source are electrically in contact, and we may have current flowing from the source to the drain in this way. Also, for this device, there is a simplified symbol which is used in digital electronics that is similar to the one of the PMOS, of the NMOS device, with this dot on the gate terminal. Also, in this case, we have that the source is the terminal at the highest potential, the other terminal is the drain, and the gate is the control terminal. Here, the control quantity is the voltage between the gate and the source, and the current flows in the exiting the drain. So this is a PMOS transistor. With this symbol used in digital electronics, it is intended that the bulk is connected, is implicitly connected to VDD, that is to the highest supply, to the highest available voltage. So this is equivalent to the full symbol with the bulk connected to VDD, like the symbol that we have introduced for the NMOS transistor corresponds to the full symbol with the body tied to ground. Okay? Now, if this is clear, we can go on discussing the electrical, we have already introduced the symbols, discussing the electrical properties of this structure. For this purpose, let's consider we will start discussing the properties and the characteristics of the N-type device. We will assume that the body is connected to the source, and we will consider as external input variables the gate source voltage, so the voltage which is applied between the gate and the source, and the voltage which is applied between the drain and the source. In order to describe the behavior of this device, we basically discuss how the current flowing through the gate and the current flowing through the drain behave while varying VGS and VDS. So basically what we will get is IG as a function of VGS and VDS, and ID as a function of VGS and VDS. So actually, let's start from IG. Since, as we have discussed, between the gate is a metal plate that is separated from the semiconductor by silicon dioxide, which is a very good insulator. Under static condition, we don't have any current, we cannot have any current flowing from the gate through the gate terminal. So basically, we have that IG is equal to 0 for any value of VGS and VDS. And this is very good news, because it means that in order to drive this control port of the transistor, we do not need any to supply any current. Supplying current means to dissipate power, so it means that we can keep the voltage of this terminal at the value we want without static condition supplying or sourcing any current. Actually, since this structure, as we have discussed before, behaves as a capacitance, so in the end, if we go back to our physical picture, we have that we consider the top view of this structure basically is we have here the gate area, we have the contacts, drain, this is the drain, this is the source contact, this is the gate area, and if we want to complete the sketch here, we have the body terminal, so this is the top view. Actually, this area with a certain length and a certain width corresponds to the surface of parallel plate capacitor, so it's reasonable to assume that looking at the gate terminal, this structure can be regarded as a capacitor with a gate capacitance that is proportional to the width times the length to the surface of the parallel plate times the permittivity of silicon dioxide, and then divided the thickness of the oxide. Okay, so the input port, for the input port, the gate current is equal to 0 for any value of the gate voltage and of the gate source voltage and the drain source voltage, and in static conditions, under dynamic conditions, the structure behaves as a capacitance proportional to the width times the length of the gate area. Now let's discuss what happens at the drain port. That is, again, let's consider our transistor, our N-type NMOS transistor. Let's apply gate source voltage between the gate and the source, and let's apply drain source voltage. Let's sweep the drain source voltage and see what happens to the current ID flowing through this structure. It is actually the current ID flowing in the channel of the MOS transistor. For this purpose, let's plot here. Let's consider the plane with the drain source voltage in the x-axis and the drain current in the y-axis, and let's plot the ID versus VDS characteristic as a function of the gate source voltage. Actually, for different values of the gate source voltage and the drain source voltage, the device operation changes in a significant way, and the 3 operating regions can be identified. First of all, when we have that the gate source voltage is less than a technology-related quantity that is called threshold voltage, VTH, threshold voltage, what happens? When the gate source voltage is below the threshold voltage, we have that ID is basically equal to 0. It's not exactly equal to 0, but it's very, very small, regardless of the drain source voltage. So basically on our plane of the characteristic course for VGS smaller than the threshold voltage, we have that for VGS smaller than VTH, we have that the current flowing through the device is 0. When this happens, basically between the drain and the source, the transistor can be regarded as an open circuit or as an off switch, and we say that the transistor is in the off region. So this is the off region. Then what happens when we apply a gate source voltage that is larger than the threshold voltage? Actually, we have to distinguish two cases. The case in which we have that VGS is larger than the threshold voltage and VDS is relatively small, less than VGS minus the threshold voltage, and the other case in which VGS is larger than the threshold voltage and VDS is also larger than VGS minus VTH. Let's start discussing this case here with VDS smaller than VGS minus VTH. Here, the expression of the drain current is ID equal to factor beta, which actually depends. Beta can be written as mu times the per unit area capacitance of the gate oxide times the aspect ratio W over L of the gate area. All these mu and Cox are technology related, and W over L is a design parameter, times the drain source voltage times VGS minus VTH minus VDS divided by 2. Actually, if at the beginning we forget this VDS divided by 2 in the parentheses, this is more or less the expression. We have VDS times beta times VGS minus VTH. This expression resembles the expression of a conductor in which the current is proportional to the voltage across the conductor, and the proportionality constant is the conductance measured in Siemens. Conductance that is basically 1 over the resistance. So we can identify all these terms with the conductance or the reciprocal of the resistance, since we will call this operating region the on region, we will call this the on resistance. So in other words, as far as we can neglect this minus VDS over 2 in the expression of the current, we can say that for VGS larger than the threshold voltage and VDS small enough, the transistor behaves as a resistor with a resistance R on given by 1 over beta VGS minus VTH. So with a resistance, a resistor whose resistance depends on VGS. In other words, it means that for small values of VGS just above VTH, we will have that the resistance will be smaller, so it will be higher, that means a small slope, while we increase the VGS voltage, we get that this resistance becomes smaller and smaller, the conductance becomes higher and higher. So this is for increasing VGS. And if VGS is high enough, the conductance becomes so high to be close to a short circuit. In this plane, the behavior of a short circuit between drain and source corresponds to the vertical axis, no? VDS equal to 0 for any value of ID. And increasing VGS, we get that the transistor between drain and source behaves as a resistor with a smaller and smaller resistance, something which resembles more and more a short circuit. For this reason, we can say the behavior of the device is the one of a short circuit or a non switch. We call this operating region the on region. Okay? So we call this operating region the on region. In the on region, for VDS very, very small, the transistor can be regarded as a resistor with a resistance inversely proportional to VGS minus VTH. If we go on increasing the VDS voltage, what happens? It happens that the minus VDS over this minus VDS over 2 term in the expression of the current is no longer negligible, and so the overall behavior of the current is parabolic. So basically, we have that these characteristics tend to bend in a parabolic way. So actually, we would have the equation of a parabolic curve. Let me try to sketch it in a slightly better way. Actually, these would be parabolic curves. Okay. When we reach the vertex of the parabola, which are actually all the vertices of the parabola at different VGS are aligned, since this corresponds to VDS equal to VGS minus VTH. This is for different VGS. When we reach the point that corresponds to the vertex of the parabola, that is VDS equal VGS minus VTH, what happens? Based on this equation, based on the equation that we derived here, we should have that the current should decrease parabolically in this way. By the way, this is not what happens in practice. What happens in practice is that above this, by the way, before going on, this region for VDS smaller than VGS minus VTH, as we have said, is the on region that we have highlighted in green. When we increase VDS over VGS minus VTH, what happens? It happens that the current does not increase anymore while increasing the drain source voltage. So it remains more or less constant. It saturates to a constant value that in any case is related to VGS, increases for increasing VGS. This operating region in which the current does not increase anymore with VGS is called the saturation region. Okay? If we want to get the expression of the current in the saturation region, well, we have simply to plug VDS equal to VGS minus VTH in the expression of the current in the on region. What we get is beta times VGS minus VTH times VGS minus VTH minus 1/2 VGS over VTH, that is VGS minus VTH divided by 2, and what we get is beta 1/2 beta VGS minus VTH squared, constant with VDS and just depending quadratically on VGS. So in other words, in this region, which is called, as we have mentioned, which is called the saturation region, we have that the current remains saturation constant with VDS. Actually, this is not fully true, since small dependence on VDS is still there, and to describe this very slight dependence on VDS, we have to add this term in which this lambda is the channel length modulation factor, which in transistors is in any case quite small, which means that these curves in saturation are not exactly horizontal, but they are slightly increasing like this. Okay. By the way, if we want to describe in a qualitative way the behavior of the transistor in this region, we can say that in the saturation region, the transistor behaves as a VGS controlled current source, behavior of a device that draws a current that is not dependent on the voltage across it is the behavior of a current source. Since this current source is the value of the current of this current source is related to the gate source voltage, actually this is a voltage controlled current source. It's not an independent current source, but it's like between drain and source, VGS controlled current source. Okay, so in short, what can we say about these characteristics from an application point of view? This is the global picture of the three regions: off region, on region, and saturation region. From the practical point of view, we can say that in the on and in the off region, the transistor behaves as a voltage controlled switch. More precisely, a switch that is off when the gate source voltage is below the threshold voltage and is on when the gate source voltage is sufficiently high and the drain source voltage is relatively small. So we have this behavior that we have described. These two operating modes, open circuit off switch for low gate source voltage, on switch small resistor tending to a short circuit when the gate voltage is high enough, are the operating regions, these two operating regions are exploited in digital electronics to implement voltage-controlled switches. On the other hand, the operation of an MOS transistor in the saturation region is exploited to implement voltage-controlled current sources that can be used in analog electronics as amplifiers. By the way, in this course, we will not cover analog electronic circuits, so let's say that we will not consider the saturation region anymore. Okay, now let's repeat the analysis for the PMOS transistor. Actually, for the PMOS transistor, what we can say is that if we consider the structure of the PMOS transistor in which the source is the terminal at the highest potential, the drain is the terminal at the lowest potential, and the current comes out from the drain, like this, what we can see is that the characteristics of the PMOS transistors are quite similar to those of the NMOS transistors that we have derived so far, provided that the drain source voltage is replaced with the source drain voltage, positive on the source and negative on the drain. The gate source voltage is replaced with the source gate voltage, positive on the source and negative on the gate, since in PMOS devices, the gate is always at a potential which is lower than the source, and the drain is at a potential which is lower than the source. Having said that, we have that for the gate voltage sufficiently high, that is the source gate voltage smaller than the threshold voltage, the PMOS device is off. For a gate voltage sufficiently large, that means fixing the source voltage for a gate voltage low enough, and for a small drain source drain voltage, the PMOS transistor is in the on region and it behaves as small resistance or short circuit. When we have the source gate voltage larger than the threshold voltage and the source drain voltage larger than the source gate voltage minus the threshold voltage, we have also for the PMOS device the operation in the saturation region. Okay, so this is what we have just discussed. Now let's see how these characteristics can be exploited in digital electronics, assuming to have digital signals as the gate signals, as the signals applied to the gate of an MOS transistor, in which digital information is associated to the at the high logic level to a voltage equal to the positive supply voltage, and at the low logic level to a low voltage corresponding to the reference voltage. So we assume that VG, the gate voltage of our transistors, either NMOS or PMOS transistors, is a logical is a voltage VG that represents a logical signal, and we discuss what is the behavior of NMOS and PMOS devices. Actually, assuming that we have an NMOS device with the source at the reference voltage, when we when we have that the gate signal is high, that is gate voltage equal to VDD, for what we have just said, we know that the NMOS transistor is on and behaves as an on switch, small resistance between the drain and the source, or possibly something which approaches a short circuit. On the other hand, if we have that the gate is low, corresponds to a low logic level, we have that the gate voltage is 0 and the NMOS transistor behaves as an off switch. On the contrary, if we consider a PMOS device, which is driven by the source gate voltage and in which the source is assumed to be connected to VDD or to high voltage, we have when the gate voltage is also high, that means also connected to the supply voltage, the source gate voltage is 0, since the source is assumed to be always high. The gate is also high, so the source gate voltage is 0, and the PMOS device is off. So for a high gate voltage, for a high level gate voltage, the PMOS device is off, while for a low level gate voltage, the PMOS device is on. Okay? So the NMOS is on at the, for a gate input at the high logic level and is off for a gate input at the low logic level. On the opposite, the PMOS is on for when the gate voltage is low and is off when the gate voltage is high. If we want to describe in a simplified way the behavior of the MOS transistor, but including and taking into account that when on the MOS transistor is not ideally a short circuit, we can add in series to the VGS controlled switch described before a resistance which represents the finite non-zero on resistance of the switch of the MOS transistor when it is on. And the same can be done clearly also for the PMOS transistor. To be more precise, also in the on state, or in the off state, we cannot regard the MOS transistor as a real open circuit, since the current flowing between the drain and the source also in the off state is not exactly 0, but is equal to a small leakage current. So in the off state, we could represent the device as a current source with an imposed current that is fairly independent on the drain source voltage and is also typically very small in the femtoampere to picoampere level that flows between the drain and the source, or between the source and the drain in a PMOS device. These currents are very small, but let's say that in more advanced technologies are not so small, so maybe they are not in the femtoampere level, but they are in the picoampere level, or even in the nanoampere. Femtoampere means minus 10 power minus 15, picoampere 10 power minus 12. It can be in the picoampere level, or also tens or hundreds of picoampere, and for large circuits with billions of transistors connected to the supply, they could give rise to a current drawn from the supply which is not negligible at all. Okay, now that we have introduced the MOS transistors, let's see how these devices can be used to implement logical functions, combinational functions, in particular Boolean functions, in an electrical way, using signals, voltage signals, which encode digital information, as we have introduced before. The simplest gate that can be conceived is the gate which implements the NOT function, that is called it's also called inverter. This gate is the simplest possible CMOS gate, which is made by PMOS transistor as a pull-up device that connects the output of the gate to the positive of the supply. Here we should always remember that these symbols means that we have a battery between the positive and the reference. We have a PMOS device connected between the positive and the output, and an NMOS device connected between the output and the negative of the supply. The gates of both the PMOS and the NMOS devices are connected together, and the voltage between the gates of the two devices and the reference is actually the input voltage of our gate. So this is V in, while the output voltage V out is the voltage that we have here, V out, between the output terminal and the reference. Let's discuss why this device, how this device behaves as a NOT gate. Actually, when we have that the input voltage is high, so let's suppose here let's start with the case in which we have the input voltage V in, which is low. That means we have the input shorted to ground. In this case, we have that the source gate voltage of the PMOS device is equal to VDD, so the PMOS device is on, while the NMOS device, which has a gate source voltage equal to 0, is off, is in the off region. As a consequence, we have that the output is connected to VDD, so the output voltage is VDD, which corresponds to a logical 1. And the NMOS device is off, the output is connected to VDD and corresponds to a logical 1. Okay? Like this. On the other hand, when the voltage of the input is high, we can consider this case. Actually, this voltage here is V in equal to VDD. That corresponds to a high logic level. We have that the PMOS is off, so the output is disconnected from the supply, while the NMOS is on, that connects the output to the ground, which as a consequence, the output voltage is 0, which corresponds to a logic level, to a low logic level. So when the input is high, the output is low. If we summarize the behavior in when the input is low and when the input is high, we can see that the output takes exactly the value of the complement of the logic value of the input, and so the function which is implemented is a NOT function. So this is actually an inverter. Now let's describe a little more in details the operation of this circuit, considering that what happens when the input voltage sweeps continuously from 0 to VDD, not just considering what happens at V in equal to 0 and V in equal to VDD. Actually, what can we say? When V in is equal to 0, we have that the NMOS device is off, NMOS off, and the PMOS is on, as we have discussed before. Then what happens when I increase the input voltage? When I increase the input voltage about the threshold voltage VTH of the NMOS device, I have that the NMOS device starts conducting with a drain source voltage which is rather high, so we have the NMOS in saturation, we have the NMOS in saturation, and the PMOS still in the on region. Due to this fact, we have that some current flows from the gate. The current in the gate is no longer zero. We have a voltage drop across the PMOS transistor, so we have that the voltage, the output voltage, tends to decrease. The output voltage is basically VDD minus the voltage drop across the PMOS, and so since this voltage drop becomes non-zero, the voltage tends to decrease. Then when the output voltage decreases, becomes less than VDD minus VTH. Basically, we have that both the PMOS device and the NMOS device are in the saturation region. The N is in saturation and the P is also in saturation. In this region, we have that the output voltage is very sensitive to variations of the input voltage, and it drops to zero with a very high slope. Then when basically the voltage V out becomes smaller than VGS minus VTH of the NMOS device, we enter, the NMOS device enters in the on region, so we have the N that becomes on and the P that remains in saturation. And finally, when the gate voltage increases, we have that the P is completely turned off, P becomes off, and the NMOS is fully on. And in this case, we have that the output is forced to zero very effectively. As we have already mentioned, the precise voltage in which this transition happens is strongly dependent on the supply voltage, on the operating temperature, and is also affected by the technology-related parameters very much. So actually is difficult to predict the exact value at which we have this transition. For this reason, we identify a range of input voltage values below VIL, which are identified as low logic values, and the range of values above VIH, which can be identified as high logic levels values, and the values in between are considered to be undefined and are not associated, cannot be associated to any useful digital information. Actually, to decide when the looking at this characteristic, to decide when we pass from a region in which we can reliably say that the output state is high, we can reliably say that the output state is low, we consider the point in which basically the slope of the trans characteristic is minus 45 degrees. That is when a variation of the input gives rise to the same variation in the output voltage. Below this value, we say that we are in the stable high state when the variation of the input is attenuated in the output. Similarly, when we are over the other threshold, we can say that we are in the input is recognized as high. On the other hand, when we are in this region, when the slope is larger than 45 degrees, we cannot decide what is the logical level. So we are in this gray area. Okay. This is something that we have already described and discussed in general with reference to the electrical characteristics of digital gates. Okay, now if this is clear, let's discuss, let's extend this concept and see how it is possible to implement more complex functions. In particular, we will see the NAND and the NOR Boolean functions with more than 2 or more inputs, taking advantage of CMOS switches. Actually, the idea is to replace the single pull-up switch that is used, that is present in the CMOS inverter, with a network of switches so that to be connected either in series or in parallel, so that to implement logical functions. The same for the pull-down network, that should not include just a single NMOS switch, but a network of switches connected in series and in parallel to implement specific functions, specific logical functions. Actually, one important remark is that in the pull-up network, we can just use PMOS devices, while in the pull-down network, we can just use NMOS devices. Let me try to explain why. Let's focus on the pull-up network. If we have in the pull-up network a PMOS device, this is VDD, and this is I don't know, this is a generic load here. This is a pull-up device. When I turn on the pull-up device by forcing a gate voltage low, the pull-up device is clearly in the on region. We have the gate source voltage. This is the source gate voltage, which is equal to VDD. VSG is equal to VDD, and the device is fully on and behaves as a low resistance R on that drives the output voltage up to the supply voltage. So a good high logic level. On the other hand, if we try to do the same, we try to use an NMOS device in the pull-up network, that's supposed to try to do this way. So this is VDD. Never forget that this symbol means that here we have a battery, and here we have our NMOS device with source, drain, and gate. Suppose that we want to drive the output high. To drive the output high, since this is an NMOS device, we need to force the gate voltage high. But if we force the gate voltage high, the highest gate voltage that we can apply is the supply voltage. In this case, since the control variable of the NMOS switch, which basically decides the conduction of the switch on or off, is the gate source voltage. If I put the gate to a high voltage, I have that if the source voltage is low, clearly the device is turned on. But in this configuration, when the output goes high, the source voltage is no longer zero. So in the end, we have that the source voltage increases as well. And when the source voltage increases, we have that the gate source voltage, that is VGS equal to VDD minus Vout, decreases as well. And if the VGS voltage decreases so that to become less than VTH, the NMOS switch turns off. So in practice, since when the source voltage approaches VDD minus VTH, the transistor is turned off. We have that in order to have a gate source voltage larger than the threshold voltage, the output voltage should be less than VDD minus the threshold voltage. It's always this way. So in using an NMOS switch in the pull-up network means that the output voltage cannot go high to VDD, which is what we need to have a full high logic level 1, which corresponds to VDD, but corresponds to a degraded output voltage level, that is VDD minus VTH. It means that the next gate that is connected here will not have a full high logic level, and so in the end the digital information is corrupted, is partially corrupted. We do not have the expected noise margin. For this reason, this is not possible. It is never used. Is never used in CMOS gate. So no NMOS devices in the pull-up network. In a similar way and with a very similar reasoning, we can say that in the pull-down network, we can just use NMOS devices and we cannot use PMOS transistors. Okay? Another important comment: in this structure, we need to make sure that the pull-up network is on, that is, provides a connection between the supply and the output, only when the pull-down network is off, and vice versa. The pull-down network can be on only when the pull-up network is off. Otherwise, if we had a condition in which we have both the pull-up and the pull-down network on, we would have a short circuit between the supply and the ground. That means a very high current flowing through the devices that could easily damage and destroy the device themselves. So actually, it is important that when the pull-up network is on, the pull-down is off, and vice versa. Now, having said that, how can we implement Boolean functions? In particular, we will see NAND and NOR functions taking advantage of this structure. Actually, the idea is to connect MOS transistors either in series or in parallel. When we connect devices in series, basically we have that the series of the device can be considered as on if and only if both the switches are on. If we have two NMOS devices in series, as shown here, which are driven by digital gate signals A and B, we can say that this pull-down network effectively connects the output X to ground if and only if both A and B are high. So if A and B are high, X is pulled down. In all the other cases, that is, if either A or B are off or both of them are off, so basically this condition is expressed by not A or not B, what happens is that the output X is actually disconnected from the reference voltage. Since it is also not connected to the supply voltage, it is not connected to anything. It means that its voltage, its logical state is not defined. It can be, from a physical point of view, it can be influenced by the external conditions. Actually, what we have is that the output, we have a small capacitance, and immediately after we go in this state that is called the high impedance state, we have that the current in this capacitance is zero, and so the voltage across this capacitance remains the one at the previous state. Possibly, since this is an extremely weak high impedance node, any external disturbance or even a small leakage current can easily either discharge or charge this capacitor to a value that is neither high or low. So let's say that in this case, we say that the output is in a high impedance state and is not well defined. Actually, if we want to get an output voltage at the high state in this condition, what we could do is to connect a resistor between the supply and the output node. Actually, this would be a pull-up resistor, a pull-up network made of a resistor. And actually, when we have, in this case, that either the switch A or the switch B is off, so these three cases that we are highlighted here, we have that the current I is zero. We have that the voltage drop across this resistor is zero, and the output voltage is VDD. By the way, this is not the approach which is adopted in CMOS gates. We will see that also this approach can be useful, and actually is the one which is exploited in open drain gates. By the way, this is not the one that we use, that we adopt in CMOS digital gates. And the problem is that this resistance RPU cannot be too low. It's typically larger than the resistance of a non-switch, and this worsens the delay of this kind of gate. And another problem of this structure is that when we have the low state to be forced, here we have a non-zero current flowing through the gate. So for this reason, this is not the solution that is employed in CMOS gates. The idea is to include in the CMOS gate a pull-up network that connects the output node to the supply only when in the cases in which the pull-down network does not connect the same output node to the ground. And we will see in a moment how to do this. By the way, let's go on with our overview of structures consisting of MOS transistors in series and in parallel. If we have two PMOS transistors in series, as depicted here, we have that the output node X, in this case, is forced high if both A and B are at the low logic level. So if not A and not B, high is forced high. This is because PMOS transistors are on. PMOS transistors on when their gate voltage is low. So when both the gate voltage of the first and the second PMOS transistors in series are low, we have that the output voltage, that both the two switches are on and the output voltage is forced to 1. In the other two possible cases, if either A or B are, or both of them are high, we have that the net current flowing through the pull-up network is 0, so the output node is disconnected from the positive of the supply, and since there is no other connection between the output node and the negative, the output node remains in a high impedance state. Okay, so basically the message is that switches in series can implement AND function. So when the connection either to the of the output either to the negative or to the positive is active, when both the two switches in series are on. So when the first switch is on and the second switch is on, that means for the NMOS switches, when both the gate signals are high, for the PMOS switches when both the gate signals are low. Okay. On the other hand, when we have switches in parallel, in this way, the connection between the output node and the negative or the positive is performed with either one or the other two switches is on. So when switch number 1 is on, or when switch number 2 is on. Since the two switches, in this case NMOS switches, are on when their gate signals are high, we can say that X is low, X is pulled down when A or B, are high. Okay? It's interesting to observe that in the pull-down network, since in pull-down network we can just have NMOS switches for the reason that we have already highlighted, NMOS switches are on when the corresponding logical variable is high. So we can just have switches that are turned on for a high logical variable. On the other hand, in the pull-up network, since we can only use PMOS switches, we can just have switches that are on when the corresponding digital signal is low. Okay? When we have two PMOS switches in parallel, in particular, the pull-up network is active when either one of the two switches are on. That means when not A or not B. When not A or not B, then X is high. In all the other cases, that is basically when both A and B are high, the pull-up network is completely off and the output is disconnected from the supply and is in a high impedance state. So what is the idea that we can exploit to get a full logic gate? We can consider a pull-up network and a pull-down network that are active for a complementary set of input. For instance, if we take the pull-up network consisting of two parallel PMOS switches that connects the output to the supply for when either one of the two inputs is low, that is, when the inputs are 0, 0, 0, 1 or 1, 0, it's sufficient to have at least one 0 to connect it to 0, and we devise a network that forces the output low only when both A and B are high, and this is clearly a pull-down network made of two NMOS devices which are force the output low only when both A and B are high. If we put them together, so if we connect the same output X to the pull-up network consisting of two parallel PMOS switches and the pull-down network consisting of two series NMOS switches, well, we have a gate that forces the input high for when we have at least 1 0 basically, and forces the input the output low when we have both the inputs at 1. And actually, what is the function? What is the name of this logical function? Actually, this is a Boolean function that corresponds to the NAND A, NAND B. Basically, X is A, NAND B. So in this way, we can implement an AND function in CMOS. Actually, the same approach can be adopted for different functions. So here we can analyze step by step and see that actually this gate that we have derived behaves as a two-input NAND. When we have the inputs that are 0, 0, basically we have that the PMOS are on and the NMOS are both off, so the Y is 1. When we have inputs 0, 1, we have that at least one of the PMOSes is on and one of the NMOSes is off, so the output is connected to the supply but is disconnected from ground, so the output is high. The same if we change A with B. When we have both the logical signals high, we have both the switches in the pull-down network high, which force the output voltage to 0, which corresponds to a low logic value, while the pull-up network is disconnected. Okay. Following the same approach, we can describe what happens with this gate that is actually we can sketch a truth table also in this case, A, B, Y. Consider possible cases 0, 0, 0, 1, 1, 0, and 1, 1. When we have both A and B 0, we have both the PMOS transistors on, both the NMOS transistors off, so the output is connected to the supply voltage. The out is VDD, which corresponds to a logic 1. On the other hand, when we have, for instance, A equal to 0, we have that and B equal to 1. We have that the one of the PMOS transistors is on, the one connected to A is on, and the one connected to B is off, while the NMOS transistor driven by the signal B is on and the other is off. So in conclusion, now we have the pull-down network that is globally off, disconnects the output from the supply, so here the output is not connected to the supply, while we have the pull-down network on that forces the output to 0, and so the corresponding logical value of the output is 0. We can see that when we exchange the inputs, it is the same, and when we have both the inputs high, clearly we have both the pull-down transistors on and both the pull-up transistors off, and we have 0. So in conclusion, the logical function which is implemented by this gate is two-input NOR. Okay? How can we do if we want to implement a 3-input NAND? Well, basically, the idea is quite similar. It's sufficient to put 3 MOS transistors in series which keep the output low if and only if all the inputs are high, while can have a pull-up network made of 3 PMOS transistors in parallel, like this. This is the output voltage Y, A, B, and C. Why, when we have any of the inputs at 0, this pull-up network, when we have either not A or not B or not C, this pull-up network forces the output high. So in the end, the behavior of this gate is like a 3-input NAND gate. Okay. By the way, we can also implement, we cannot implement all possible logical functions with a single gate with a pull-up and pull-down network. By the way, we can also implement other possible functions. It's not possible to implement any function since we have this limitation that the NMOS transistors are only active with signals at the high logic level. The PMOS transistors are active with signals at the low logic level. By the way, we can also implement operations that are more complex than a single NAND or NOR operation. And we can also try to devise a general procedure to implement logical functions in CMOS. For instance, we can start from the pull-down network. We can start from the pull-down network and devise a switch configuration that makes it possible to force the output low, so to force not out when it is to be forced low. That is, if we want to implement this function when C and A or B. So the AND operation means switch is in series. So if we have a switch driven by the logical signal C that is on when C is high, in series with another structure that consists of 2 or means parallel 2 switches driven by the logical signals A and B, this network connects the 2 nodes, is equivalent to an on switch when either A or B is high. The overall network from Y to reference, the overall network consisting of 1 series switch in series with 2 parallel switches is active exactly when we have C and A or B. So this pull-down network is suitable to force the low state when needed to implement this function. To implement the pull-up network, well, we can apply de Morgan's rules to this expression. We get that this is not C or not A or B, that is not C or not A and not B. We can read this expression as a PMOS switch driven by C, which is on when not C is true, in parallel to PMOS switches in series, which are on, the series is on when both not A and not B. So in total, we get a gate which implements the function out. Yes, actually, this is the name of this is out. Out is not C and A or B as requested. Another approach, we can start from the pull-down network and implement the pull-down network as we have described. Then we can derive the pull-up network, considering that all the switches connected in parallel of the pull-down in the pull-down network correspond to PMOS switches connected in series in the pull-up network. So here we have A and B in parallel. Here we have the PMOSes A and B in series, and the connection in series C with the parallel of A and B becomes, this connection in series becomes connection in parallel. So if we exchange series with parallel and parallel with series, we can we can get the topology of the pull-up network, which is needed so that it is operated in a complementary way with respect to the pull-down network. That is, not to have the pull-up network and the pull-down network on at the same time. Okay, let's stop here.